Outside our solar system, the galaxy is a violent place. Supernovas and deep space explosions constantly blast high-energy cosmic radiation across the void. But Earth, along with our neighboring planets, remains largely protected. We are encased inside a massive magnetic bubble called the Heliosphere, which absorbs about 3/4 of those deadly cosmic rays before they can reach us. Because we live deep inside this protective bubble, we have a strict geometry problem. We cannot step outside the solar system to see what our own shield actually looks like. For decades, consensus held that the solar wind formed a comet shape with a long trailing tail. Then Voyager and IBEX data shattered this model. The tail didn't exist. Instead, it collapses, splitting into two distinct curled jets, forming a deflated croissant. Losing the comet model leaves us with a critical blind spot. To accurately calculate how much cosmic radiation penetrates our solar system, we have to map our exact borders. The heliosphere is entirely powered by the sun. Back in 1958, astrophysicist Eugene Parker calculated that the sun continuously exhales a stream of charged particles in all directions, a phenomenon known as the solar wind. These diagrams show the sun's 11-year magnetic cycle. At solar minimum, left, magnetic lines are neat and dipolar. At solar maximum, right, they become tangled and chaotic. This twisting field changes the strength of the solar wind ejected outward. This simulation reveals why the croissant shape forms. A dense, slow-moving particle wave mixes with a hotter, energetic set called pickup ions. These hot particles rapidly escape the boundary. As they bleed out, the heliosphere shrinks, deflating the tail into two jets. The edge of our solar system is a volatile collision of bleeding fluids. Observing it requires an instrument built specifically to look through that chaos. 1 million miles away from Earth, suspended toward the sun at the Lagrange 1 point, the environment is dark, isolated, and stable. This is the operating theater for the Interstellar Mapping and Acceleration Probe, or IMAP. Its primary mission is to definitively resolve the boundary debate. The real challenge for IMAP is distance. The edge of the heliosphere is more than 10 billion miles away, and the probe is parked firmly near Earth. This illustrates IMAP's solution. At the chaotic border, colliding ions become energetic neutral atoms. Without a magnetic charge, they travel in perfectly straight lines to the inner solar system. IMAP catches them, tracing their trajectories backward to generate a precise 3D wireframe boundary map. By catching these incoming messengers, we can plot the structure of a barrier 10 billion miles away without ever leaving the stability of Earth's orbit. Understanding our exact geometry within the galaxy has direct, practical consequences for planetary defense. The sun regularly ejects massive waves of glowing plasma. When these sudden solar storms slam into Earth's magnetic field, they can overwhelm our power grids and fry global communications. Because IMAP sits a million miles upstream, it intercepts these plasma waves before they reach us. That position provides a critical 30-minute early warning system for Earth's infrastructure. Looking outward, the heliosphere's exact thickness dictates how much deep space radiation enters our solar system. Astronauts traveling to Mars or establishing lunar bases need that precise math to survive long-term exposure. Once we know exactly how our own magnetic shield operates to foster life, astronomers can use this blueprint to identify other star systems with similarly strong defenses. Solving the mystery of the heliosphere's shape provides the coordinates of our solar system's shielding, defining the final, physical borders of humanity's cosmic home.